Good morning, Internet friends, and welcome to Dev Update number 3. If you remember, the last couple updates have been on running a single election and verifying the artifacts generated in that election. Today I want to show you the last part of Milestone 1, which is an automated test suite that generates a bunch of random election configs, runs the corresponding elections, and then tries to verify them. And it checks that for honest elections, the verifiers always agree and it succeeds, and it also simulates a few different hypothetical attacks and checks that the verifiers catch those attacks. Let's look at the code. If you want to follow along, the process is basically the same as before. You clone the ElectionGuard Cardano repo, go into the Milestone 1 test directory, and go into a Nix develop shell. Now there are two entry point scripts. There's election.sh, which does the same thing as the previous videos showed. It runs a single election and verifies it. But now we also have tests.sh, which will generate a bunch of random election configs, run lots of elections, and then assert things about the output files. And it's only fast because I've already run it before. If you run it for the first time, this might take up to a couple hours to run all of the elections. There are basically two kinds of tests in here. There are the ones that test honest election runs, which are the straightforward kind where all the verifiers should agree on the result, and probably the most important assertion I make about those is that the final tallies always match the initial config, and here you can see the code for that. And that basically just tests that the whole encrypting and tallying workflow works properly. The second group of tests is all about simulating various ways that someone might attack the election and making sure that the verifiers can always catch the attack. You can see each one has a name and it has fields called who and when, and who specifies which election role would perform the attack, and at runtime it'll just randomly select one of the containers with that role. So if it says device, it'll select one of the encryption devices to corrupt. And then when says at which point during the election the attack should be performed. And at that point the corrupted device will run attack.py and the function for that attack. And then after that, the rest of the election will continue, and at the end, it will assert that the verifiers should catch the attack and fail to certify the election. Let's look at a particular test election as an example. We're going to look at test F5FBB, which I know has the device mutate submitted ballot attack in it. So here you can see that the election goes normally up through the vote commit all step, and then it randomly decides to corrupt encryption device number 2 and has it run this function in attack.py. There's also a more detailed attack.log in the private data of the corrupted device, so we can check that to see what exactly it did. After picking a random encryption device to corrupt, the test also picks a random ballot to mess with, and within that ballot, it picks a random crypto field to mutate. And that just means it's going to change one of the hex characters to a different hex character. So in this case, it changes character 27 from a 5 to a 7. And then it just overwrites the file in place. Then the rest of the election continues as normal, and we check whether the verifiers catch the difference. You can see there are 4 different verifications here posted, what'll be on chain in the future, by 4 different parties. There's one by the admin, which takes the place of the official tally summary from before. And then each of the guardians also posts one, and then other independent verifiers can additionally post their own. If they're being honest, all of these verifiers should agree, so we can look at any of them, but let's look at Verifier 1. The most important thing to check first that is checked on all of the attack elections is that gather election should be false, which means the verifier noticed that something is wrong and doesn't certify the election. If we look in the set of errors here, you can see the first thing is that the particular submitted ballot that was messed with fails, which is good. And it fails with this very long cryptographic error message. But the important thing is that it says it's an invalid proof and it won't accept that ballot. The corresponding spoiled ballot also failed verification. And then, of course, a bunch of other nodes in the dependency DAG also fail because they depend on that ballot. Because none of the cast ballots were messed with, the final tally actually proceeded as normal and still works fine. And that's exactly what we want. We don't want the whole election to be derailed just because one ballot was messed with, but we do want to be really sure that we can tell it was messed with. The automated test suite basically does this a bunch of times and tries to find some example that'll falsify my assertion that every time there's an attack, the verifier should notice it. So it'll try corrupting different devices, it'll try messing with different encryption fields inside each ballot, and so on. One thing you might have noticed if you looked carefully at my list of attacks is that this handles the case where the cryptography is broken, but there's no attack that says what if the encryption device decides to correctly encrypt the wrong vote. So what if, for example, I'm trying to vote for Alice and the encryption device says, okay, here's your encrypted vote for Alice, but it actually just encrypted a vote for Bob. And the answer is that that can't be detected in this system, because in order to detect that, you'd have to save a record of who everybody voted for, and that would break ballot secrecy. So ElectionGuard has separate mechanisms to test for this. One is the Benelo challenge, and the other I haven't talked about yet is risk limiting audits, and we'll get to both of those later. And that brings up one more important point, which is that these tests aren't meant to be comprehensive. They're more meant to just catch simple coding errors, like if I wasn't doing one of the checks I should be doing in one of the cryptographic fields, this would hopefully find it. But they're not meant to simulate the real behavior of self-interested actors and test the game theory or anything like that. This has been Dev Update 3. Join me next time and I'll talk about publishing election artifacts over IPFS. In the meantime, happy holidays and be excellent to each other.